Hello, my name is Zbigniew Kurikowski. I'm a senior ML engineer at Virtus Lab, and today I'm going to be talking about a case study of a solution we did for one of our clients that involves enhancing product recommendations through use of real-time data streaming. And I'm going to go through the problem. I'm going to explain what are the considerations for that problem and present the solution, and then we're going to validate this solution against some metrics. Okay, so first let's talk about the opportunity. What was the problem and what we were trying to solve? Our client, a world retailer, runs an online shopping platform which has a critical aspect to it. Everything that the user sees is personalized based on their past purchase history. This is explained on the diagram here. We have a client that accesses the web page or an app, and then this goes through inference platform that, based on past client behavior and ML model that was trained specifically for this use case, will enhance what user sees on the page based on past purchases of that client. So this is the vertical part, and then on the just to the side we can see how the model gets trained. So every aspect of user behavior, including sales history, is passed through a data warehouse, which is then used to train an ML model using a feature store. So this solution worked pretty well. There's only one problem with it. Going through data warehouse and then a feature store, it takes a significant amount of time. It could be days or in some cases week, because obviously data warehouse is not well suited for operational use case like that. What's the opportunity here? Let's look at the left side of the diagram, where we can see that at the same time when the data goes into the data warehouse, it also goes through a Kafka topic that contains all information about user behavior on the page or on the app. So it's an obvious opportunity, right? We can leverage that data to move from a batch data processing and batch model training into something more real time. The idea is that we would use this Kafka topic to build a solution that's more real-time, that has a slower latency between user actions and adjustment of the content that they view on the page. So what are we really interested in? What's our goal? So it's pretty simple. We have a target which is called click-through rate, and which expresses the amount of interactions over impressions. What's interaction? Interaction is a user interacting with a page or an app, where impression is a user seeing a particular piece of content on the app or on the web page. It's pretty simple, but why haven't we decided on something more complicated? There are other metrics like revenue per basket or revenue per customer, so why haven't we done that? Its answer is pretty simple. In a very complex ecosystem like that, it's quite difficult to deliver a real-time margin estimate for a huge retail platform like that. So instead, we settle on something simpler that can be calculated on the fly. The whole system is built around that, and so we can keep the latency minimal. Okay, so what about the data? Like I said, client has a web page and an app and potentially some on-site use cases. So what is the data? Data will be all user actions on the page, including what the user sees, what browser they're using, what they click on, what's the content of their basket. So all of that will go in, and let's talk about the size of this data. This would be around a few thousand events per second just for a single location on the page. If you want to include multiple regions that the client operating in, and we include app and then web page, this could grow into tens of thousands and potentially into hundreds of thousands of events per second. So scalability is a crucial issue here. So let's move over to other requirements. What else do we have to consider here? So first of all, this has to be an operational online system. So we have a strict SLA on when the model gets updated and how fast the user can view the content that's generated by the model. So obviously the model can't be too complicated because it has to run very fast. And another requirement is that all data is fully recoverable, meaning that there is no situation in which we would lose any of the data that we processed in the result of a failure. Additionally, user identity remains hidden at all times during the processing, and there is no bias introduced into the model based on non-critical data, meaning the sole data that goes into the model is the past sales history, as well as obviously users' interactions on the page. We are basing our model only on relevant characteristics. We are not basing this on, for example, the zip code from which the client is coming from, or their browser agent. This goes into ethical AI and how we can achieve that. And also, this personalization is only presented to users who have explicitly agreed to it through use of cookies. Next, let's talk about what we chose as a basis for our solution. And it's a toolkit called Apache Flink, which is a stream processing software, which has which was built from ground up with few tenets in mind. So first of all, Flink has strict correctness guarantees, meaning that all the results are reproducible and consistent. It has layered APIs, which means that it can be used from various programming languages and is applicable to teams of various skill sets. It has operational focus, meaning that whatever you build in can be very easily put into production. And also scalability. So you can go from a minimal use case POC to something that builds your core business strategy. And another tenet is performance. So there is no compromise in regards to latency, throughput, and cost. Additionally, we chose Flink because it offers excellent integration with many data sources and sinks, most importantly including Kafka, which is a critical piece of infrastructure here. And Apache Flink is an open source software and it's available under Apache license, which is also an important aspect to our decision. So let's talk about why Flink is important, what features of Flink benefit to this use case. Okay, so first of all, Flink has a capability called stateful processing, which means that Flink doesn't look at individual events. If, of course, it still can, but it goes beyond that. Flink can process multiple events in the same context, meaning that it can look at multiple consecutive events for the same customer or from the same system and make some logical decision based on that. So for example, you can run aggregation, window functions, joins, all that happens between multiple events. So your processing isn't limited to one event, it goes wider than that. Okay, and then this is a very important piece of capability here, and Flink offers multiple ways to solve that through backends for storing the state. So there are a few options ranging from in-memory state storage to key value database like RocksDB. Okay, I've talked about stream processing, but what is stream processing really? For Apache Flink, there is really no distinction, honestly. Apache Flink will treat both batch and streaming use cases in a very similar way, meaning that Apache Flink can be used to both use cases. But for our use case, it was critical to use the streaming use case. So the difference between batch and streaming is, for Flink, is only a difference between finite or bounded or unbounded streams. The processing is still pretty much the same no matter what's the nature of data processing. This is critical because Flink can be used apart from this use case. Flink can be used as a base tool for many solutions we can build for our client. Okay, and there's something called event time processing. So what is event time processing? So in a naive implementation of stream processing, the data will be processed whenever it arrives, meaning that if you have some logic that takes in the events and makes some operations on them, this will happen whenever the application is running, which is not great because we want to have reproducible results. We don't want to depend on the application being completely aligned with the timeline of the events, meaning that we want to process those events irrespectively of the timeline in which they were delivered. This goes great for local development because we have a replicable development environment, meaning that a developer can pretty much go back in time to any point in the past, and then use this event time processing to get a fully reproducible result. Okay, and this also is important for something called root cause analysis. So whenever there is a failure on the production, we want to have a reproducible way of understanding what was the root cause for it. And that obviously Flink solves that. One other important aspect for Flink is that it's available under many APIs and languages. So and it's available to many user personas, from a BA analyst through a data scientist into a data engineer. And no matter how your team is composed, you can still use Flink using different APIs. So there is the obvious and the most simplistic way of using Flink is through SQL. But then if you want to get into more advanced use cases, you can go into programming level interfaces using the data stream API, which is available in Java and Python and Scala. Okay, so what solution have we presented to the client? So on the diagram, you can see that not that much has changed. We still have a data warehouse, we still have a feature store, but then we've extended the left side of the diagram to include Flink. And Flink takes in the raw events from Kafka and then creates a feature topic, which consists of data points that can be directly used within the online training service. And as you can see, both training and inference are online. Online is fed through events coming from the feature topic, and then the online training service and inference service exchange information through something called parameter store. So whenever the online training service receives a new event and retrains the model based on that, it updates the model parameters within the store to be retrieved by the inference store, and then the inference service can make decisions based on this newly available information. This means that the content can be adjusted in seconds. Obviously, it might be not the most efficient to retrain the model on every event, but we can choose an appropriate amount. We can retrain really on every single event, or we can retrain on every 5, 10, 15 events, depending on the use case, which gives great elasticity to the solution. And since the online training service and the inference service are separate, then you can also use different tooling for both. Okay, and how have we deployed that? So we've deployed that through a very convenient and relatively easy to use tool, which is called Flink Kubernetes Operator, which allows you to automatically supervise and manage Flink applications on your Kubernetes cluster. It's very easy to deploy and very easy to manage, and it provides a control plane that manages the applications with minimal input, minimal amount of tinkering from your side. And we had some generally good experience with this tool. And also, the operator can be used with both on-prem and on-cloud Kubernetes clusters, which is an obvious advantage. Let's talk about resilience and how it impacts our application. Flink has a built-in capability which is called checkpointing, which will either run on a very small schedule, meaning seconds to minutes, or continuously depending on the configuration. What is checkpointing? You can think about checkpointing in terms of pretty much save points in video games. You can save the state of the application at any point. This happens automatically, obviously. And then if our application would crash, you can retrieve the state and go back to that point in time, and then catch up with the processing. This brings great resilience to the Flink application. Additionally, everything in Flink can be run in high availability deployment, meaning that there is no single point of failure. Okay, and let's talk about auto-scaling, which is also a feature of Flink. So why auto-scaling? pretty much one singular but very important aspect, and that's cost. Autoscaling will lower the amount of operational cost you have to put into running a Flink application, because Flink will monitor all internal processing as well as load on individual pods when running on Kubernetes, and it will adjust the amount of resources both within the application itself, and also you can use horizontal pod scaling to adjust the amount of resources in the whole on the whole for the whole Flink application. And let's go into monitoring. Flink offers excellent real-time statistics on all internal operations for every step of processing. It provides a very elegant UI, which you can use to troubleshoot and monitor the application. Obviously, there are some use cases. For example, we had this, it was a situation for us where we wanted to use external monitoring, for example, New Relic or Splunk, etc. And in our case, this tool was App Insights, and it was very easy to integrate internal Flink monitoring capabilities with an external App Insights solution. And this way we achieved a uniform monitoring solution that allows us to monitor the whole deployment from a single place. Okay, so I'm nearing the end of the presentation, but there's one little change. So actually the client had a change of mind in terms of some aspects of our application, meaning that they didn't want to go all into the model parameter store, because the inference service that was used for inference wasn't easy adjusted to a solution like that. So we decided for something simpler, where the data from Flink is saved directly into the feature store and then used in conjunction with other features from the data warehouse to train the job. And this training job happens every few minutes, which is good enough. It's very close to real time. Obviously, depending on the use case that you might have, this few minutes might be entirely okay, or it might be not enough, and that's adjustable based on which architecture you use. But in the case of our client, few minutes latency between clients making an action on the page and then content being adjusted is enough. And client was pretty happy with the solution. And let's go into the results. So over a span of 7 days when the model was running, this is you can see a diagram for one of our tests that we've conducted. We've seen a 35% uptick in click-through rate for the duration of A/B trial. You can see a baseline and our solution, and you can clearly see the difference and the advantage of using a system like that. Why not train this in batch though? Why is it important not to train in batch? Because you can see that based on the data available on the diagram, there is no model drift. Model drift is a concept that when the model parameters will start being stale, and the model itself will be adjusted to all data where the distribution of user actions will change over time, and this will result in subpar performance. And we wanted to avoid this happening, and this is exactly we achieved exactly that. There is no model drift because the model is adjusted continuously, and the client always sees the best content they can, no matter what time of day or night. Okay, this is the end of the presentation. Thanks very much for listening, and enjoy your time on the conference.